So is the screen visible to you? Is it visible now? Can you please unmute and speak so that I need not change my window. Is it visible right now? Sorry, unable to speak. Okay, is the screen visible right now? Okay, fine, fine. Okay, so we can start today's session. So this is week 10 on problem solving in gate metallurgical engineering. So past weeks we have been solving previous year questions. So on the same level we will be solving certain questions today as well. So and a few problems from previous years, and like whatever sessions I've already taken, we will be solving a few problems from them plus a few new problems so that we will get a revision sort of thing. So on that note, let us start today's session. So first question is, at equilibrium spacing in a crystalline solid, which of the following is true for net interatomic force and potential energy? So the option is force is 0, potential energy is 0, force is 0, and potential energy is minimum. Force is minimum, potential energy is 0, and force is minimum, U is minimum. So the question is, at equilibrium spacing in a crystalline solid, which of the following is true for net interatomic force and potential energy? So anybody from the audience knows the answer to this question? So yeah, please tell me. Huh? Yeah. Yeah, so that is the right answer. For those of you who didn't understand the concept, the actual thing is that suppose we consider two atoms. Those two atoms are come together, are brought together from infinity, and initially there will be an attractive force between them. So this is the attractive force part, and as the interatomic separation goes on decreasing, at one particular point repulsive forces also started and reaches a maximum value, and we have a distance r0 at which the attractive force, as you said, exactly balances the repulsive force, and hence the net force will become 0. Therefore F is 0 in this particular question. And since it is an equilibrium position, what happens? So equilibrium means that it will be a state with minimum potential energy. We all know the Gibbs equation, right? So based on that equation, so at equilibrium point, the net energy will be minimum. And this E0, that is the net energy, is known as the bond energy. So therefore, from this we can say that F will be 0 and U will be minimum. Is this question clear to all of you? Others who are in the chat, please respond. Like we have a few students here. Yeah. One person said yes. Is Sanjit the one who answered? Okay. Who answered the question initially? One person had actually answered, right? Who was it? Okay, that person is not responding right now. So I'll have to move on. Therefore, the answer will be F is 0 and U is minimum. So the next is also a very simple question. As temperature increases, the electrical resistivities of pure metals and intrinsic semiconductors vary as follows. So either both of them will increase or both of them will decrease, or one increases or the other decreases, or vice versa. So please give me your thoughts on what is possibly happening in metals and intrinsic semiconductors with increase in temperature. So can anybody answer? Anyone here? What happens to the conductivities or resistivities of metals and semiconductors as temperature increases? Anybody? It's a very simple and direct question, I believe. If anybody can put their answer in the chat window, that is also fine. Anybody, what happens to the conductivities and resistivities of metals and semiconductors with change in temperature? Anybody? If nobody is answering, I'll have to call out by names. So, does Sanjeet know the answer? Mr. Sanjeet? Now, what about Kamesh? Am I? Okay, I don't know the answer. Okay. And what about the other person who's in the chat? I'm not able to read his name. So, okay, so I guess none of you know the answer. Then I myself have to maybe explain. So the thing is, as temperature increases, in case of metals, their resistivity will increase, and in semiconductors, their resistivity will decrease. So we can say that when we're saying with respect to conductivity, metals will have a less conductivity at higher temperature, and semiconductors will have more conductivity at higher temperature. So what is the reason? So what happens is that in case of conductors, as temperature increases, the atoms will start vibrating heavily, and these vibrations will lead to collision between the electrons, and because of the increased number of electron collisions, the pathway for the electron flow will be disrupted, and as a result the material won't be able to conduct as efficiently as it was able to do at lower temperature. Therefore we can say that as the temperature increases, the resistivity of the metal increases. And we can also say that there is a possible other question, how what is the variation of coefficient of resistance, and if something is directly proportional, we can say that it has a positive correlation. Therefore it gives a positive temperature coefficient of resistance, and at higher temperature the conductor's resistivity increases and therefore conductivity decreases. But what happens in case of semiconductors? You might also be thinking that in case of semiconductors also similar vibrations may taking place, therefore that material should also show increased resistivity. But for semiconductors we know that there is a band gap, so there will be electrons in the valence band, there will be empty space in the conduction band, and whenever sufficient energy is provided, electrons from the valence band jump to the conduction band. So that is how conductivity or electron flow happens in case of semiconductors. At high temperature what happens is that more number of electrons will start gaining enough energy, and more electrons will be excited from the valence band to conduction band, and therefore even though the collisions increase, these collisions will be superseded by the number of carriers created, and therefore as the number of carriers increases, the resistivity decreases, or we can say that the conductivity increases. Also we can say that semiconductors have a negative temperature coefficient of resistance because it is inversely proportional. So is it clear? As temperature increases, electrical resistivity of pure metals increase and intrinsic semiconductor decreases. So rho m stands for metal, rho s stands for semiconductors. Hence we can say that in case of resistivity of, sorry, this option is wrong I feel. So the option will answer will be option C. Resistivity of huh, resistivity of metals will increase and the resistivity of semiconductors will decrease. So is it clear for all of you? If you have any doubts, please do ask me, then only I'll be able to explain. So okay, Mr. Kamesh is actually responding. What about the other two people in the chat? Are they able to understand? I'm not actually getting any response. Okay, one person replied he is able to understand. Yeah, okay. Thank you so much. Sorry. Okay. So the next question is, if D is the interplanar spacing of the planes HKL, and if suppose D is the interplanar spacing of HKL, then the interplanar spacing of the planes NH, NK, NL with N being an integer is. So option A is D, option D by N, ND, and D by N power 2. So anybody? If you know the answer of what is the equation for interplanar spacing, then you will be able to answer this question. Can anybody solve and tell me? So for a cubic system, the interplanar spacing equation is given by D is equal to A by root of h square plus k square plus L square. In the same equation, suppose instead of HKL, we are substituting NH, NK, NL. What will be the answer? That is the condensed form of this question. So what will be the answer? Can anybody solve and tell me? Okay, I'm not getting any response. Let me see. Option B. One person has written option B. So the answer is option B. Yeah. So, for those who didn't understand this question, we know that the interplanar spacing for a given plane D is equal to A by root of h square plus k square plus L square, where A is the lattice parameter and HKL denotes our plane under consideration. Suppose, then what happens for the plane NH, NK, NL? We are substituting, let it be D prime A by N square into h square plus k square plus L square. Therefore, what happens if this is substituted by this part? It becomes D by N. So is it clear for all of you? The answer is option B, D by N. So is it clear for others how they got D by N? Okay. So, yeah. Next is a peak in X-ray diffraction pattern is observed at 2 theta is equal to 78 degrees, corresponding to the family of planes 311 for an FCC metal. When the incident beam has a wavelength of 0.154 nanometer, the lattice parameter of the metal is approximately, we have been given four options and out of that we have to select. So I will give you a clue. You have to use two equations in this basically. One is the same, that is D is equal to A by root of h square plus k square plus L square, and the other one is 2D sine theta is equal to n lambda. So I'll give you a few minutes. Please try to solve. Now the gate examination is actually nearing and it's necessary that you are able to solve such questions by yourself. So please take 2 to 3 minutes and try to find out the answer. So the clue is you have two equations. D is equal to A by root of h square plus k square plus L square, and 2D sine theta is equal to n lambda. So based on these two equations, please try to solve these questions in 2 minutes, please. Somebody joined, I think. Okay. So for the person who just joined also, please try to solve this question. So it's an XRD related questions. Like many questions actually come from this particular region. Therefore, please be familiar with it. We have to use two equations. One is d is equal to a by root of h square plus k square plus l square, and the other one is 2d sine theta is equal to n lambda. Based on these two questions, please try to answer this. Hello? Yeah, hello, please tell me. Yeah, please tell me. Okay, fine, 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 fine. Yeah, thank you so much. Sorry. For others, have you started solving and anybody got the answer? Please unmute and speak. If you've got the answer, else I'll explain. So lambda is given to you, theta is given to you, HKL values are given to you. Based on that, you have to substitute into equations. D is equal to a by root of h square plus k square plus l square, and 2d sine theta is equal to n lambda. And you have to find the value of A. The lattice parameter of the metal is asked, so you have to find the value of A. Anybody got the answer? 0.4 nanometers. That is the correct answer. What about the others? Are you getting the same answer? Okay, since none are responding, I think I'll have to present the answer as well. So, so first is from the Bragg's law, we know that 2d sine theta is equal to n lambda, where n is the order of reflection, and unless and until otherwise mentioned, we always take the order of reflection as n is equal to 1. So in this particular equation, what all is given to us? Lambda is given to us, sine theta can be found out. 2 theta is given, theta is equal to then 39 degrees. And if you substitute, you will get the value of d. And once you get the value of d, it can be substituted in this equation. That is a by root of h square plus k square plus l square. And if you substitute, you will get the value of a. So how do we actually solve? So 2 theta is given, and theta is equal to 39 degrees. Lambda is equal to 0.154 nanometers. And from Bragg's law, as I mentioned, 0.154 is equal to 2 into d sine 39. And on solving, d is 0.1223 nanometers. Is it clear up until here? Okay, I hope it's clear. And once d is obtained, we can get d is equal to a by root of h square plus k square plus l square. It was told that it is a plane of 311. So we are substituting the d value as well as the HKL values. Therefore, 0.1223 is equal to a by root of 3 square plus 1 square plus 1 square. How much will be this? This will be root 11, right? 0.1223 into root 11 will give us the value of A. Therefore, the value of A is 0.405 nanometer. Hence, the option will be zero point 0.4 nanometer. From here, the answer will be option B, zero point 0.4 nanometer. So, is it clear for all of you? Is it clear? What about the other person, Sanjeet? Okay, I'm hoping it's clear to him. Yeah, please tell me. Okay, so I'll just have to move on. If you have any doubts, please do stop me in between and ask. So this is somewhat of a not conventional type of question. So a single crystal FCC metal is subjected to a sufficiently large tensile stress along the 110 direction to activate some of the slip systems. Which of the following slip systems will be activated? This question was actually solved in previous class, but I got mails that few students found it difficult. That is why I'm discussing it again. So the question is, a single crystal FCC metal is subjected to a sufficiently large tensile stress along this given direction. to activate some of the slip systems. Which one of the following slip systems will be activated? So that is the questions, and a set of four options are given to us. So we know that a slip system will be a combination of a direction and a plane. So this direction and plane combination is given to us, and we have to find out what is the condition for activating systems. So slip systems will be activated when the Smith factor is non-zero. Therefore, we have to calculate the Smith factor for all these four options. So, does anybody know what is the equation for Smith factor? Yeah. So, Smith factor is given by m is equal to cos phi cos lambda. And phi is the angle between normal to the given slip plane and the 110 direction. And lambda represents the angle between the given direction and the 110 direction. So whenever we are calculating cos phi and cos lambda, one thing has to be kept in mind. Phi will be the angle between the given plane. So in options, many planes are given to us, then is curved brackets, right? So the given slip plane and this direction, that will be phi, and lambda will be between the given direction. That is, in option we have many direction, this direction and this particular direction. For phi is the angle between normal to the given slip plane and direction. Lambda represents the angle between given direction and the 110 direction. That is the angle, that is the direction in which the tensile stress is applied. So now we have to calculate the value m for each of these four options. So how do we do that? First, we need to find out how to find the normal to a given slip plane. The normal to a given slip plane is actually that particular direction. Suppose we want the normal to a plane 111, that will be the direction 111. That is like a shortcut that we do. Suppose you want to find the normal to say 1 bar 1 bar, it will be the direction 1 bar 1 bar. So is that clear till now? Okay, I hope it's clear. And now we have to find out the values of this cos phi and cos lambda, right? And only thing that we have is two directions. So how do we, if suppose two directions are given to us, how do we find the angle between those two directions? That is found out by using this equation. We can say theta is equal to cos inverse u1 u2 plus v1 v2 plus w1 w2 divided by root of u1 v1 w1 sum squares and u2 square plus v2 square plus w2 square. So this is the first direction that we have, and this is the second direction that we have. And provided we have both the directions, the value of theta can be calculated. And we know phi should be between so and so direction, lambda should be between so and so direction. And if we know what all directions are to be considered, we have to find out the value of theta. So that will be found out using this particular equation. And using the same equation, we can calculate this for both phi as well as for lambda. So this is the normal. Whenever we are studying the Smith factor, you might be familiar with this kind of a diagram. That is, a material is being pulled in particular direction, and there will be a slip plane. There is a normal to the slip plane. So normal to the slip plane is actually the slip direction itself. So based on these two values, and so here what we have to do is phi is the angle between the applied direction and normal to the slip plane, and lambda is between the applied direction and the slip direction. So based on that, we have to calculate the value of phi and lambda. So can you please calculate the values of m for these four options and tell me in which one of the following slip system is activated? So we have to calculate m for all four options, and which option gives us non-zero value, that will be the answer. So can you please calculate? This is actually 2 mark question, so you can take slightly more time compared to the XRD related questions. So calculate m value for options, and whenever you find a non-zero answer, that will be your answer. So slip system will be activated in that particular plane and direction. So can you please calculate? Option A, B, C, and D. Please calculate the value of M and let me know. Sorry, since it's the flu season, I also got a flu, so that's why you're getting continuously disturbed by my cough. Sorry for this inconvenience. So, has anybody started calculating? So, if you have started calculating, please respond. Otherwise, I'll project how to calculate. Option B. So, is this the same answer that Sanjit is also getting? Option B. So, I think I'll have to present. So we know the equation that in order to find theta, suppose we want two directions, we can calculate this using this equation. So phi was between normal to the given slip plane and the force direction, and lambda was between the given direction and the force direction. So based on that, so first what was our option? Our first option was 1 bar 10 and 111. So for 1 bar 10 and 111, how did we calculate? So 1 bar, 1, 0 and 1, 1, 1. So here we were doing 1 bar. 1. So B is to U1, V1, sorry, U1, U2, V1, V2, W1, W2 divided by root of 1 bar square plus 1 square plus 1 square. So are you getting the same equation for the first one? For phi, and for lambda we have to take between the given direction and the force direction. So first option M, is everybody getting the same one as 0? So if you are not understanding, so one first we have to take 111 and 110. Then we have to take 1 bar 10 and 110. So when we are calculating, in both cases, 110 will be there, right? 110 is here and 110 is here also. First one, based on the direction, we have to say 1 bar, 10 and 111. So that is the U1, V1, U2, V2, W1, W2 part. So is the M correct for the first option? Everyone is getting the same? So similarly, we have to calculate for each option. And Kamesh had mentioned that option B is the answer. Are you getting 1 by root 6 as the answer? Yes. Okay, fine. So for option B, we got 1 by root 6. And whenever we were calculating similarly for option C and option D also, we got that the phi and lambda values were 0. And since the Smith factor became non-zero only for option B, this is the slip system where the slip was actually activated. And therefore the answer to this question is option B. So I hope it's clear for all of you. Like for Kamesh, I'm sure it's clear because he was able to answer. So what about the other person? Is this particular question clear to you? He's not responding, it seems. Okay, so I'll have to move on probably. Okay, so the answer is option B. That is 0 1 1 direction and 1 1 1 bar plane. So that is the answer to this particular question. So the final question is, in polymers such as epoxies, creep resistance can be enhanced by increasing the bulkiness of side grooves, increasing the cross-link density, adding of plasticizers and annealing. So please take care that in polymers such as epoxy, so for thermoset polymers and thermoplast polymers, there will be multiple answers will be matching. So first you need to identify whether epoxy is a thermoplast or a thermoset. So what is an epoxy actually? Thermoplast or thermoset? Okay, are you sure? Huh. Yeah. So we'll see the answer now. So what is creep in case of polymers? In case of metals, we know that under a constant load at room temperature, they will start elongating. When you are seeing from a polymer's perspective, it is the tendency of the polymer to distort under external loads as temperature increases. We know that polymers will be in a highly coiled semi-crystalline state, right? So as the polymer experiences the static load, the chains will start uncoiling and they will slip past each other as the stress is applied. So this phenomenon is temperature dependent, and increased temperature will decrease the secondary bonding between the chains. That is why this uncoiling happens. Yeah, somebody has unmuted. Please speak. It's okay. It's okay. It's okay. So, first we'll see about crystalline polymers. So, in case of crystalline polymers, there is a high degree of secondary bonding between the chains. Therefore, they have more creep resistance than amorphous polymers. So, whenever you have getting a question as to whether which of the following statement is true, whether it's an amorphous polymer and a crystalline polymer, we can say that crystalline polymers are more creep resistant. The reason is that there is a high degree of secondary bonding between their chains. Then, in case of thermoset versus thermoplast, so thermoset polymers, as you said, what happens? The creep resistance of these material increases with the amount of cross-linking between the chains. The cross-link also what happens is that as the cross-link increases, the glass transition temperature increases, and as the glass transition temperature increases, what happens? The sliding or the straightening of chains under the applied load reduces, and we can say that the creep resistance of the material increases. Therefore, thermoset polymers such as epoxy should be fully cured. So what happens as we cure the material, the secondary bonding or the cross-linking between the chains increases, right? Therefore, when we are increasing the curing, what happens? The creep resistance of such materials increases. Also, one other point is that for thermoset polymers, creep resistance increase with their molecular weight. So if you see the options here, now we realize that epoxy is a thermoset polymer and the answer will be increasing the cross-link density. Here nothing is mentioned about the molecular weight, but in case an option is given that about with increases with molecular weight, that option will also be correct. It need not be that only a single option will be correct. There could be cases where multiple options are correct. And also thermoplastics, what happens, they are less resistant to creep compared to thermoset polymers, and their resistance is controlled by the arrangement of these chains. So crystalline and semi-crystalline materials are more creep resistant than amorphous or glassy polymers. uh, Also, one other thing, generally for all across all type of polymers, suppose a polymer is having a large side group or a large pendant group, and it will cause more chain entanglement, and because of the chain entanglement is increased, we can say that the creep resistance is also increased. So that is about creep in polymers. So one thing you have to keep in mind, we have to first realize whether the material under consideration is a thermoplast or thermoset. Comparing thermoplast and thermoset, thermoplast will be less creep resistant compared to thermoset polymers. Also in thermoset polymers, either we can increase the molecular weight or we can increase the cross-linking between the chains. Cross-linking can be increased by increasing the curing. Also comparing crystalline, semi-crystalline and amorphous polymers, crystalline will be more creep resistant and amorphous polymers will be the least creep resistant. So is this question clear? Yeah. What about Kamesh? Yeah. So I wanted to ask you, is there any specific topic that I should focus on for the coming week since gate is already approaching? Is there any specific topic that you want a recap of or any specific set of questions related to physical metallurgy or mechanical metallurgy? Certain questions that you're not able to solve? Yeah, please tell me. Phase diagrams and heat treatment. So, are you actually attending another sessions for thermodynamic part? Yeah, I think there are sessions for thermodynamics, weekly sessions. Is anybody taking that sessions now? Like usually what the case is that each tutor like us will be given a particular set of questions. For me they have given physical metallurgy and mechanical metallurgy. For another person they have allotted thermodynamics. So phase diagram and those things comes under thermodynamics. So is that session actually going on? Were you able to attend those sessions or has it stopped completely? Okay, fine, fine, fine. So tomorrow I have a session, I think, but then I won't be able to cover this. But for the upcoming sessions, I'll try to include questions from heat treatment and phase diagram also. Yeah, thank you. Any other suggestions? Tomorrow, I think maybe. Huh? Okay, fine, fine, fine. Tomorrow they have not there. Maybe it's not there. If it is there, they will intimate you by mail. In case a session is fixed, it will be intimated to you. Yeah. What about Kamesh? Do you have any suggestions on specific topics that I need to include for the upcoming sessions after New Year so that you can be more focused towards the gate preparation part? Any suggestions that I should include? Metallurgical thermodynamics. So, many people are actually asking me through this mail also. I think you people should collectively drop a mail to NPTL asking about specific topics in metallurgy because actually sessions were planned weekly for metallurgical thermodynamics. I think maybe it's discontinued now, and once you ask NPTL they might give us permission to take up questions related to that. So if possible try to take an email directly to them asking for metallurgical thermodynamics, and still if they're not responding then I'll also try to include at least the most important portions from those. Yeah, thank you Kamish. Yeah, so that's all for today's week. I hope whatever we discussed today was useful to you. So thank you so much for joining. So we'll meet in the next class. Thank you. You may leave now. Yeah, thank you.